last time we got into obviously energy, and we talked about a couple different things in terms of energy. We talked about delta H, which is the change in enthalpy. And as I mentioned, it's probably the most common way in chemistry that you kind of see is a reaction exothermic or endothermic. And we also obviously talked about that as well. Obviously, exothermic means that heat and energy is released. And endothermic means, obviously, we talked about heat and energy is absorbed. And one way that you could calculate the delta H, as we talked about, is if you're just given a reaction, you basically could go to a table and you could look up the delta H values for all of the products, which is on the right-hand side of the arrow, and all of the reactants, which is on the left-hand side of the arrow, and basically take the difference. And this has to do with a lot with what we talked about in terms of state function, right? So what's important is sort of where you start and where you end. Final state minus initial state. And as we talked about, when you think about a chemical reaction, your products is really your final state. And your reactants, which is what you start with, is your initial state. So to calculate the delta H, as we saw there for a particular reaction, you again take the delta H of your products minus the delta H of your reactants. Remember that the one thing that you do have to do is you have to take into account the coefficient in the balance equation. So when you look up those values, if that thing, say like water, for example, had a 2 in front of it, you would have to multiply the value you find in the table by 2 when you go into this equation. Remember that if it is an exothermic reaction, delta H is going to be a negative number. Delta H will be a positive number. We also saw that with our energy diagrams that we looked at as well. When we have reactants that are higher in energy than our products, energy is released overall, and that's an exothermic reaction. When your reactants are lower in energy than your products, in terms of energy on those energy diagrams, energy has to be put in, and it's an endothermic process. We talked about specific heat capacity and an equation Q is equal to ms delta T. Once again here, Q is heat or energy, and usually has values of joules or calories. M is our mass, which has units of grams. Delta T is our final minus our initial temperature. Remember, that's one of the few things in chemistry that we typically leave in degrees Celsius. And then S is our specific heat capacity, and that has units, the 3 units, joules per gram per degree Celsius, are calories per gram per degree Celsius. Once again, here, a relationship that you should know: 1 calorie is 4.184 joules. That, by the way, is also the specific heat capacity of liquid water. So for liquid water, which is a value that you should know as you journey through chemistry, the specific heat capacity for that is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. As we saw in that table, if it is in a different state like ice or steam, it will have a different value. So for water, it's closer to 2 for each of those things. You can plug it into here and solve for any of those things, Q, M, S, delta T. Remember, though, that it is the temperature value or the change in temperature that's really going to determine whether or not this reaction is going to be exothermic or endothermic, as that is the only place where you can get a negative to basically happen. And remember that when people sort of gain energy, we see their temperature go up, right, because they're gaining energy. And when they release energy in an exothermic, we do see a drop in their temperature as well. So the relationship between exothermic and endothermic for Q works the same way. Q is negative for exothermic, and Q is positive for an endothermic process. So you can look at Q or delta H if you have either one, and the sign of it, again, will let you know whether or not it's endothermic or exothermic. The very last thing we talked about was the idea of sort of the transfer of heat and energy. And a lot of times, like I mentioned at the end last time, we could use something like just water and a thermometer, and we could follow the change in the temperature of the water to relate it back to whatever was put in the water. For example, we talked about there a piece of metal. And if you take a hot piece of metal, or by the way, if you take a cold piece of metal, it doesn't necessarily matter. But if you put a hot piece of metal into some room temperature water, again, in that situation, remember that heat flows from hot to cold. So if the metal is hotter than the water, the metal is going to release its energy to the water. It's going to be exothermic for the metal, endothermic for the water. By the way, if it was opposite and the metal was actually colder than the water actually would release its energy to the metal, and the metal would pick up the energy as well. Remember that because we know everything about the water here, we know specific heat capacity, we can follow the temperature and all those good things. We can then figure out something like how much heat was absorbed or lost by the water, and we could relate it to our metal with this relationship that Q of the metal is equal to minus Q of water. It is the exact same amount of energy that's either gained or lost by the water as the amount of energy that's either gained or lost by the metal. The only difference is the sign. For the exothermic person or process, it will be a negative value for heat and energy. For endothermic, it will be the same number, but it will be positive. Any questions on any of that stuff there? All right, so I think we stopped right at an example of this after we kind of went through one. So why don't you give this a go? You got a 110 gram sample of a metal at 55 degrees, 55.5 degrees Celsius. It raises 150 milliliters of water from 23 degrees to 25.5 degrees Celsius. What is the specific heat capacity of the metal? So take a few moments there and work it out, see what you get. Okay, let's take a look. So this is really the same situation we were talking about at the very end. We have a metal here, and we know the mass of the metal here is 110 grams. We have an initial temperature here of the metal, which is 55.5 degrees Celsius. We're going to put it into some water here, which has a volume of 150 milliliters. It has an initial temperature before the metal goes for a swim of 23 degrees Celsius. After we pop the metal in there, it will now have a 25.5 degrees Celsius temperature. And over here, we are looking for the specific heat capacity of the actual metal. So in this particular case, a couple of things we want to think about. Obviously, if we look at the initial temperature of the metal, which is 55, and our initial temperature of the water, which is 23, we can see that the metal actually is hotter than the water. So we know that the transfer of energy and heat should go from the metal to the water. So remember, again, going from hot to cold here. So our metal should be releasing the energy, which for us should automatically tell us that that's an exothermic process for it. The water should be gaining the energy, which will be an endothermic process for it. The other thing that we talked about is obviously in this situation, when you put that metal piece in there, it will eventually come to rest at the same final temperature as the water, right? Because it's basically sitting in there. It's going to come to equilibrium with the temperature of the water. So once again, from that water information where it kind of stops, we do know the final temperature of the metal will be the same, 25.5 degrees Celsius. Now, one of the other things that we also know about liquid water is we always have the specific heat capacity of it. Again, may not be given to you in the problem, but again, that's sort of a number that you always have available to you. And again, you may have to look up some specific heat capacities on certain problems as well in a table. So if we think about our water here and the specific heat capacity sort of formula there for water, Q is equal to ms delta T. We have delta T, we have S. We don't exactly have the mass, but we do have the volume. And another number that we should know for water like we use today, is density of water is 1 gram per milliliter. So remember, if we have the volume, we know the density of water, we could actually calculate the mass of the water, which in this case would be the exact same number here, as the milliliters will cancel, and we'll end up with 150 grams of water. So that is how we can get our volume of water into grams, again, by using density. And again, that's another number that oftentimes not given to you anywhere in a problem. But if you find like, hey, I kind of need to get to grams and I have the volume of water, that's again a number that you could use. As we talked about, truthfully speaking, density does change with temperature, but if it's not an issue of that in most problems, that's a pretty safe number to use, the 1 gram per milliliter. Now that we have that sort of converted into grams, we really have everything we need to figure out, in this particular case, how much energy the water is going to absorb from that metal. So if we pop our numbers in there, 150 grams, our 4.184 joules per gram per degree Celsius. Once again, here we do want to go final temperature, which is 25.5 minus initial 23 degrees Celsius. And if we do that calculation there, we end up with a value of about 1,569 joules. The grams are going to cancel. Degrees Celsius going to cancel. That's going to leave joules as the only number we have left. At this point, I do know I'm going to use that number to kind of continue on with the calculation. So I am not going to clean up the sig figs at this point. Again, we want to maybe figure out where we should go. We are multiplying here, but remember we are subtracting here, which means we do want to look at decimal places. And when you do that subtraction, I believe it was 2.5 you ended up with. And 2.5 has two significant figures. This guy obviously has 4, and this guy has 4. So really speaking, if we were going to kind of wrap up the problem at this point, we are looking at like the second significant figure as to where we should be. Once again, I'm not going to really round at this point because I'm going to continue on with the calculation, but I do want to kind of keep that in mind for the very end. Any questions so far? So if we think about the same equation for the metal, we do have delta T. We do have the mass. And once again, we can use our water value here to figure out the Q of the metal. That is that relationship that we talked about, that Q of the metal is equal to minus Q of the water. Again, it's going to be the same amount of energy. It is just going to be the opposite sign, as in this particular case, it is exothermic for the metal. So it'll be negative 1569. And now we have sort of our missing piece there. We can now solve for S, and S would equal Q of the metal divided by M delta T, taking our negative 1569 divided by our 110 grams. Once again, here we do want to go final minus initial for the metal. So that's going to be 25.5 minus 55.5 degrees Celsius. Once again, that right there is going to hit me a negative number. That's going to work really nice with that negative number. And that again is going to turn my specific heat capacity back into a positive number, which is what it should be. So we're going to divide by 110. We will also divide by the difference between 25.5 and 55.5 in this case. And that's going to give us our specific heat capacity there of looks like 0.4754 5454. Remember here that none of these units cancel out, so they all remain. The joule stays with the number, and everything else is basically 1 gram per degree Celsius. Obviously, in this case, we do need to clean it up. So this is where knowing that we should have two significant figures here is important. So two significant figures on top. When we subtract here, that's a 30.0, which is 3 significant figures. So that's a 3 significant figures there when you subtract. And over here, that obviously is 4 significant figures. So it does look like 2 is going to be the winner in terms of significant figures. And that's really based back from this calculation that we did at the beginning. And that would take us to our 7, and that looks like a 5 next door to it. So 0.48 joules per gram per degree Celsius. Any questions on that there? So as we've been talking about, you do want to make sure you keep track of your calculations all the way through. Again, avoid rounding until sort of the end. But as you can see here, it really is the first calculation, which kind of determines where we end up in terms of significant figures on our very last one. Any questions on that or specific heat capacity? Okay. All right, this we're going to talk about just a little bit, not too much, and I think we touched upon it a little bit earlier. Again, there are 2 different sort of calories that we sometimes will come across. The calories that we were using, sort of lowercase z's, and more nutritional calories that have a capital C. And 1 nutritional calorie is equal to 1,000 of the little guys, and that is equal to 1 kilocalorie. Sometimes we'll see. One of the ways that we can measure, for example, how many calories there are in food is to use what is sometimes referred to as a calorimeter. And we can use an apparatus such as this, which is sometimes referred to as a bomb calorimeter. It's a very insulated system where we have water, but basically it works pretty much like a very standard one. We have water, we have a thermometer, and I'm going to go with we have a chocolate chip cookie there in our chamber. And we got some oxygen, some wires. We do a spark, sets our cookie on fire. Obviously, the heat then transfers to the water, temperature rises, and you use a very simple equation like we did, Q equals ms delta T. And again, you can figure out how much energy was released into the water or absorbed by the water. And you could turn those calories, lowercase calories, into nutritional calories. And you can figure out how many calories per gram, for example, was burned and stuff like that. Years and years ago in these type of classes, they would give you like a Cheeto or something like that. You'd bring like a Diet Coke can and you fill it with water and then kind of put the Cheeto underneath it and let it burn and keep the water in the can and kind of that type of thing to figure out the nutritional value. They don't do that too much anymore, but that's a very simple way you can actually do it. So this is a very good one. Again, that's similar how they get kind of those nutritional values that you find like on the back of food and labels and stuff like that. Now, a bomb calorimeter such as this, and we're not going to get too much into that in this class, but in case you come across it in the book or something like that, sometimes the calorimeter itself has a specific heat capacity associated with the actual equipment. We're not going to deal with any of that in this class. So if you happen to come across it, just kind of ignore it. But sometimes you will see in some problems like, hey, the calorimeter itself has a sort of heat capacity associated with it. That brings us, like I said before, there is sort of the caloric value found in food, and there's 3 types of food categories that we usually look at. That's carbohydrates, that's fats, and that's proteins. And if you ever look on the back of a food in a nutritional label, you typically will see those 3 things listed: how many grams of fat, how many grams of carbohydrates, and how many grams of protein are in there. And each of those has a caloric value, and that is, again, also how they sort of could calculate the calories per serving. For protein and also for carbohydrates, it is 4 kilocalories per gram. Remember, a kilocalorie is actually 1 nutritional calorie. And for fat, it is 9 kilocalories per gram. So if you wanted to sort of calculate, like on the back of your nutritional label there, how they get to those calories, you take the grams of protein, times it by 4, take the grams of carbohydrates, times it by 4, and take the grams of fat and times it by 9. And essentially you add them all together, and that'll give you how many calories you have per serving. My experience is usually they tend to round down because, they're in calories. They don't round up and stuff like that. So they typically round a little bit down. So again, that is sort of what you could do to figure out nutritional calories. Now, in the laboratory, and we're going to do this in a lab coming up, we can do calorimetry, as I mentioned the other day, by simply just using some styrofoam coffee cups. They work really well. And you stack a couple of styrofoam coffee cups. Harder to find in California because we don't sell styrofoam anymore. But all these schools are like, uh-oh, don't throw our cups out anymore. Um, so you got a little lid on it, a little hole typically in the lid. And with like the basic equipment like that, a couple of styrofoam cups, a lid, and a thermometer, you could actually calculate, the specific heat capacity of a metal. You could do an experiment like in that problem where you fill this with water, you dump in a hot piece of metal or a cold piece of metal or whatever like that. You could also very easily mix together a couple of actual reagents. Like you throw an acid and a base in there and let it do its reaction. And just by following, again, the temperature change that occurs, you can figure out the energy associated with that reaction. The reason it works well for that is most solutions are aqueous solutions, which means a majority of the solution is water, or water based. And you can use the specific heat capacity for water and get a fairly accurate value, even if you don't know the specific heat capacity for the acid or base specifically that's there. You could just use water and kind of think of it as the water specific heat capacity. Now, when you do this in a lab under constant pressure, when you measure Q, that is the same as the delta H, or the change in enthalpy. So again, with a very simple sort of tool, you could figure out basically the enthalpy or the change in enthalpy for an actual reaction. You could do any type of reaction. Like I said, you could do like an acid-base reaction. You could do like a single replacement reaction, which we'll talk about in a later chapter, where you toss a piece of metal into some hydrochloric acid and a chemical reaction occurs, makes some hydrogen gas and stuff like that. And again, just simply following the temperature change with a thermometer will allow you to do those calculations and figure out the enthalpy by figuring out the specific heat. I think we'll skip that one there. That's just an example of nutritional calories here. The last thing we're going to talk about in this chapter is thermochemical equations. And a lot of times you are given some equations, like I said before, with the delta H value. And again, that is probably the most common way that it is expressed to you. Now, when we look at the coefficients in the equation, these guys are what are sometimes referred to, and we'll talk about in a later chapter. But since this is chapter 10, they assume you already did that chapter. These guys are also known as what's known as the moles of something, and the relationship there. And what happens in a particular reaction when you have a delta H value given to you is if you do something to that reaction, it will change the delta H. And it changes based on what you do to it. So, for example, if I took this guy here, which was basically our ice melting to our liquid water, and the delta H there was 6.01 kilojoules per mole, basically. In that case, yeah. And for our purposes at this point, we could just look at it as kilojoules. So if you have an equation like this and you're like, cool, that is basically the process of melting an ice cube, right? Water in the solid state's ice and water in the liquid state's obviously liquid water. So this is the process of melting, basically. But let's just say you didn't want the process of melting. You want to know how much energy is associated with freezing water, right? And that would be this reaction reversed. So if we reverse this reaction, basically just flip it around and start with the liquid water going to the solid water, and that's basically freezing ice. Basically, what we did to this reaction is we reversed it, And how that affects the sign of delta H is we actually change the sign of it. So instead of it being positive 6.01 kilojoules, because we reversed it, it becomes negative. And that's because if you think about how you calculate delta H, like we talked about, take your products minus your reactant, which means when you reverse the reaction, your products become your reactants, your reactants become your products. The number difference is the same, but the sign changes because of it. If we started with a negative value for delta H in the first one and we reversed it, it would become a positive value. So the sign just changes. Other things that sometimes happen is, let's just say you were doing something and you're like, well, I don't need one water molecule there. I need two. So if I took that very first equation and I multiplied the entire equation by 2, I would end up with an equation that looks like this. Now, what that does to the delta H is because I multiplied the entire equation by 2, I would actually have to multiply the delta H value by 2 as well. So because it's not just one happening there, there are 2 moles of it happening. And that will get me a 12.0, we'll call it 2 kilojoules would be my actual reaction for that. Now, another very common thing that you do with these equations sometimes is maybe you are starting with this reaction here. And you're like, well, I don't need 2, but I just need 1 of those water molecules, right? So in this case, we may divide everybody by a common number. And what that does to the delta H is you also divide it by the common number as well. And that will lead you back to our original equation up on top. 1 water goes to 1 liquid water. And that will give us our delta H of 6.01 kilojoules. So if you have a delta H that's with a actual equation, and you need to manipulate it, if you have to reverse that equation, you change the sign. If you have to multiply by a common number, you multiply the delta H by a common number. And if you have to divide by a common number, you divide the delta H by a common number. Any questions on that there? Not something we're not going to get too far into in this class at all, but you will see it in 1A is when we have equations like this, we can add together multiple equations to get an overall equation. So for example, let's just say I had this guy, A plus B goes to E plus F, and I wanted to know, like, hey, what is the delta H value for this particular equation? And the only information that was given to me were 2 separate equations. A plus B goes to C plus D. I think I know the alphabet. Delta H is equal to 100 kilojoules. And maybe C plus D goes to E plus F. We'll go delta H is equal to 50 kilojoules. So basically, I want to take these 2 equations and build that equation up on top. So in this particular case, all I have to do is add these 2 equations together. When you add equations together, anything that's on opposite sides of the arrow that are the same will cancel out or reduce down. And what I mean by that, if we look here, I have a C on the left-hand side of the arrow in that one, and a C on the right-hand side of the arrow in the other one. They cancel each other out. You can kind of think of the arrow like an equal sign. Like if you subtract it to the other side, they're going to kind of cancel. I also can see I have a D on the left-hand side of the arrow and a D on the right-hand side of the arrow, and those will cancel out. That's pretty much everything that's going to cancel out in this case. Now, to get the overall reaction, anybody that's on the left-hand side of the arrow stays there. So A plus B stays there. And everything on the right-hand side of the arrow stays there. E plus F stays there. And now I have successfully sort of built the reaction I'm looking for. Now, this is a super simplified version of this. Sometimes you will have the equations not facing the right direction. So you might have to reverse them like we just talked about, which means you would have to change the sign of delta H. You may have to multiply an equation by a number, which you have to multiply the delta H, or do all those kind of manipulations we were just talking about. Now, to get the delta H for this reaction, we actually just add our delta H's together. Since we did not have to manipulate any of those equations, the delta H's are just what they are, right? We don't have to reverse the signs or anything like that. And the delta H for the overall reaction would be 150 kilojoules in this particular case. This is the super simplest version of what is known as Hess's law, which is something that you'll learn a lot about in Chem 1A. And again, it is kind of the idea of state function that it could take a bunch of these little reactions, move them around, add them together to get an overall reaction. And the total amount of energy is just adding all those steps together. Any questions on that there? All right, that wraps up chapter 10. Like I said before, we're going to take care of one little section of chapter 11, and then we're going to call it a day here. So, okay, so this is going to be kind of like, I think it's 11:11, kind of last part of 11. We're going to talk a little bit about periodic trends because we talked about the periodic table, and we can't wait till chapter 11, I think, to do it officially, because I think the lab's going to happen before we do that. So we're going to take this a little bit of time here to talk about some periodic trends. And obviously some of this stuff will kind of be filled in a little bit as we go back, obviously, to chapter 11 and stuff like that. So let's talk about some of these periodic trends. And the first thing we're going to talk about are what are known as valence electrons. And when we talk about valence electrons, there's two types of electrons that you find in an atom. And the two types of electrons that you find in an atom are core electrons and valence electrons. Now, core electrons are lower energy electrons. They are closer to the nucleus, while valence electrons are the highest energy electrons. They are the furthest away from the nucleus. Now, as we will talk about, because of that, the core electrons, if you want to think about the nucleus as we know as a positive charge, and we have these electrons moving around randomly here, electrons obviously are attracted to the positively charged nucleus. Even the outermost electrons, like the valence electrons, are also attracted to the nucleus, but there is a difference in how they are attracted. One that is closer to that positive charge is going to be held tighter than one that's further away from the positive charge. You can think of it like a magnet, right? If you had a magnet and you put something near it, really close to it, it is going to be right attracted to it, right? But if you had a magnet and you put something a little further away from it, it is not going to be dragged in really tightly to the magnet, right? Unless you move, again, the magnet closer, and that's going to cause that attraction to occur. So the difference between these two types of electrons, and one of the main difference between these two types of electrons is the core electrons, because they're held really tightly near the nucleus, they are not involved like in bonding. When we talk about bonding in chapter 12, which is up next, it is all about the valence electrons. Those outermost electrons, because they're not as close to the nucleus, they're not held as tightly, and they're easily sort of shared or easily lost in the bonding process. Core electrons, good luck to you, as we will see here in a second, trying to get rid of those electrons, move those electrons out. They're just held too tightly for that to happen. This is what is known as electron configuration. And for example, if we look at the electron configuration here for nitrogen, 1s2, 2s2, 2p3, just a preview of what this means. Each of these first numbers are basically the energy level. So the 1, or the first energy level, is closest to the nucleus. And as it goes to energy level 2, 3, 4, 5, 6, and 7, you're getting further away from the nucleus. So when we look at this here, that is the first energy level. The number on top is actually how many electrons there are. So on the very first energy level for nitrogen, there's 2 electrons. When we get to the next number, that's a 2, that's higher in energy. And this guy is also a 2, that's higher in energy. They are both on the same energy level. That is 3 electrons and 2 electrons. That is 5 valence electrons for nitrogen. They are the highest energy level electrons. Now you could write the electron configuration for an element, which we'll talk about obviously in chapter 11 at the beginning of it. But the quicker way to determine how many valence electrons somebody has is to just look at the periodic table. And if you look at nitrogen on the periodic table, nitrogen is hanging out there in group number 5, which means it has 5 valence electrons. See how that works? That's not bad. That's probably how that works. I don't know for sure, but I think. Still working this whole chemistry thing out. Oxygen right next door is group number 6. It has 6 valence electrons. Fluorine, group number 7, will have 7. Neon, group number 8, will have 8. One exception for group number 8 is helium. Helium has an atomic number of 2, which means it has only 2 protons and has only 2 electrons. So even though it's hanging out in group 8, it actually only has 2 valence electrons because, frankly, it only has 2 total electrons. So it can't have more than that. But everybody else in group 8, neon, argon, krypton, all the ons have 8 valence electrons. Just like if we go over there to lithium on the left, lithium is group number 1. It will have 1 valence electron. Magnesium is group number 2. It will have 2. And just for fun, the transition metals will also have the same number of valence electrons as the group number. When you get to transition metals, though, you just roll with the 1 through 18 numbering. So, for example, if you go where lithium is, that's group 1, beryllium group 2, and then we have SC, that would be group 3, Ti group 4, V group 5, chromium group 6, and then group 7, and we'll stop at iron there. That would be group 8. Iron actually has 8 valence electrons. So transition metals are a little weird in terms of their electrons, and again, in chapter 11, we'll talk more about that, but that's the quick way to figure out valence electrons. Very good thing to remember for bonding as well. As you can see here, the group number equals the number of valence electrons, which again are those electrons that are involved in bonding. All right, so as you go down, for example, in terms of periodic trends, we're going to kind of talk about some periodic trends here. As you go down a group, especially for metals, they tend to give away their electrons a lot easier. And if you remember when we were talking about ions, it is the metals that will lose electrons, right, and become cations. And if you look at group 1 on the periodic table there, lithium, sodium, potassium, and going down group 1, cesium, which is towards the bottom there, will lose its electrons a lot easier than lithium will. And there's a few reasons why that is. And that is because when we go to cesium, those electrons, those outer electrons, are further away from the nucleus. And because they're further away from that positively charged nucleus, they're not being held as tightly. So it doesn't take a lot of convincing for it to kind of let go of its electrons and stuff. Now, nonmetals typically will gain electrons. And in terms of most active nonmetal, upper right of the periodic table is where you find that, and that's fluorine. Fluorine is actually the most reactive nonmetal. Most active or reactive or active, whichever we want to say it, metal can be found lower left of the periodic table. And we're going to talk why that is in just a second. And let's talk about some of these things that are periodic trends. The first thing we're going to talk about is what's known as effective nuclear charge. And when you look at the periodic table and we look at an example, let's just take lithium for a very simple example. Lithium has 3 electrons. And if I write the electron configuration for lithium, it's 1s2, 2s1. On this second energy level, that is the valence electron for lithium. And here on the first energy level, these are the two core electrons for lithium, the ones that are closer to the nucleus. Once again, lithium is group number 1, and it has 1 valence electron. And once again, that is it. So if I were to draw just sort of a picture of what's going on, because lithium is atomic number 3, lithium has a +3 nucleus from its 3 protons that are hanging out there. On the first energy level, which is called N is equal to 1, there are those 2 electrons hanging out. Then on the second energy level, and I'll just draw like this. This is not accurate in the way it actually happens, but let's kind of draw it for our picture here. On the second energy level, we have our 1 valence electron. So what happens in terms of opposite attraction is this. When a positive thing and a negative thing are near each other, they're attracted to each other. The strength of that attraction actually increases with size of those charges. So if you have a +1 and a -1, they're going to be attracted to each other. But if you have a +3 and like a -3, they're going to be attracted to each other even tighter because of the larger charge. So what happens to our core electrons down here is, frankly, they are sitting right near the nucleus and that +3 charge. So those core electrons feel the full strength of that +3 charge, which means those core electrons are going to be held very, very tightly. And they pretty much are not going to go anywhere because of that. Now, when you get to the lonely little valence electron out here, it actually does not experience the full +3 charge. And that is because in its way here are these lower energy electrons. And what happens to this electron is it feels what is known as shielding. That electron is shielded from the positive charge of the nucleus by those lower energy electrons. So it's like if you're in the movie theater and you got a really nice view of the screen, and right before the movie comes, somebody sits down with a big giant hat right in front of you and shields half of the screen, right? You no longer are seeing half of the screen because of that. So this electron here on the outside is not feeling that +3 attraction to the nucleus, is actually feeling something much less than that. And you could actually calculate it, and that is what is known as effective nuclear charge. You calculate by taking the number of protons, which is 3, and you subtract the number of electrons that are in front of it, which is 2, and now that outside electron is only feeling a +1 attraction, which is still keeping it in place, but it is not being held as tightly as those 2 electrons that are like right up on the positive charge, right? They're right front row center. They're feeling the full brunt of it. So because of this effect, that's why certain electrons, like valence electrons, are not held as tightly as those ones that are closer to the nucleus, because they don't feel as strong of a positive charge to the nucleus. The general trend for effective nuclear charge on the periodic table is the Z effective will increase as you go up to the right and decrease as you go down to the left. So it increases as you go up to the right or to the right of the periodic table, because if you look on the periodic table, atomic number increases as you go to the right, which means there is a greater positive charge in the nucleus to start with, which because of that is going to drag those outer electrons in closer to the nucleus to begin with, because they're starting with a bigger positive charge, and that's going to result in those outer electrons feeling a larger positive attraction to the nucleus. Any questions on that there? Now, ionization energy is another factor that affects, what's happening. And ionization energy is the energy that's required to remove an electron from an atom in its gas phase. By the way, electrons actually come off one at a time. They don't all just pop off at once. So for example, if you took magnesium, the very first thing that would happen is magnesium would drop one electron. And that is what is known as the first ionization energy. Then what would happen is magnesium that's already lost an electron would lose another electron. And that is known as the second ionization energy. And as you could probably imagine, magnesium that's already lost 2 electrons will perhaps, probably not, lose a third electron. That is known as the third ionization energy. Do you think it is easier to remove the first electron or like the third electron? Which one should be easier? The first one is much easier. It is neutral. When we lose that first electron, as we talked about with ion size, the electron density shrinks, right? That moves those electrons closer to the nucleus, and they're going to be held tighter, so it's going to be harder and harder to remove more electrons after that. Yes, sir. Are you asking the second one would be easier? Or? No, it wouldn't be. Then the third one, yeah, you're correct. Yes. There's a few factors involved, yeah, into how many electrons it wants to get rid of. But yes, you are correct that it gets harder every time you try to remove it. So the first ionization energy is the easiest. The second electron coming off would be harder than the first. The third one would be harder than the second, and so forth. So in general, the first ionization energy, when you look at the periodic table, it increases as you go up and to the right and decreases as you go down. If you have a high ionization energy, you do not like to give away your electrons. It takes a lot of energy to remove them. If you have a low ionization energy, it doesn't take a lot of energy to get rid of those electrons or remove them. And that's what we see here. So for example, if we take a look at, this is actually the energy to remove each of these electrons. If we take a look at magnesium like we did, it's about 735 kilojoules of energy to remove the first one. It then doubles to about 1400 to pull off the second. And then you can see here for the third, you're up to 7700. That is a big jump. If you look at aluminum, first one 580, second one 1800, third one 2700, fourth one 11,000. So a big jump. So if you remember the other day, we talked about magnesium, which is group number 2. And magnesium typically forms what type of charge is group number 2? A +2 charge, which means magnesium typically will only make a +2 charge because if we write the electron configuration for magnesium 1s2, 2s2, 2p6, and that is 12, I think. That is, we got there 2 or 10 and 3s2. As you can see here, this is the third energy level. These are the 2 valence electrons. And what happens when we become a +2 charge after the first and the second, these guys are gone. These are now core electrons. And good luck trying to remove those. It takes a lot of energy to do so. It's not going to happen under normal conditions. It's not energy efficient to do so. And that's why there are certain things that make a fixed charge. Magnesium will never make anything more than a +2 charge because you don't have enough energy to rip out those core electrons. So it's going to stop at +2. Aluminum, which is group number 3 on the periodic table, has 3 valence electrons. For aluminum, 1 valence electron, 2 valence electrons, 3 valence electrons. Now you're going to try to get into those core electrons for aluminum, and that's not going to really happen under normal conditions because there's just too much energy for that to happen. So as you remember, we talked about things that have fixed sort of positive charges. This is one of the reasons for that. Again, once you remove all those valence electrons, it doesn't want to remove any of those core electrons for a couple of reasons. One main reason is if we take a look at what I just crossed out for alumina, that was magnesium here. When I cross this guy out for magnesium and I count up the electrons that are left, how many electrons are left there? 6, 2, and 2 is 10. If you look on the periodic table, who's number 10? That is neon. And that is a noble gas. That is like super stable. That's what they want to be. So the whole purpose, as we'll talk about in the bonding chapter, is for everybody to end up with the same electron configuration as a noble gas. And that's why they don't want to get rid of any more at that point. They're perfectly good and happy at that point. They don't need to rip out their core electrons to try to do that. They've now hit a pretty stable situation, and they're very happy doing so. Any questions on that? So ionization energy we usually associate with cation formation, things that make positive charges when they remove electrons. Another sort of periodic trend is electron affinity. And electron affinity is the energy change that occurs when we gain an electron. And that's really anion formation. And when you look at the periodic table, it's not a perfect trend, but it does increase as you go up and to the right and decrease as you go down. When do we see this energy change? If you have high electron affinity, that means you're probably fairly good at gaining electrons. Yeah. So if you have a low electron affinity, you're not so affinity to electrons. You don't like to gain electrons. By the way, electron affinity should not be confused with something we'll talk a lot about in the bonding chapter, which is electronegativity. And electronegativity is the ability of an atom to bring electrons toward itself. So electron affinity is the energy change when somebody gains an electron. Electronegativity is like the ability of an atom to like drag electrons towards itself. By the way, electronegativity also on the periodic table, trend-wise, increases as you go up to the right, decreases as you go down to the left. It is fluorine that is the most electronegative element you could have. So fluorine is the most electronegative element that you could have. Now, all of these things, these sort of trends, lead to what we see in terms of the size of atoms. As we go up and to the right, we have things that have a large effective nuclear charge, which is going to bring those outer electrons closer to the nucleus. We have things as you go up and to the right, which have high ionization energy, which means they do not want to remove their electrons or give them away. We have things when you go up and to the right on the periodic table have high electron affinity, which means they like to gain electrons. And when you go up and to the right on the periodic table, they have high electronegativity, which means they like to gain electrons and take other people's electrons. All of that results in, when you look at atomic size on the periodic table, when you go up and to the right, size gets smaller. So when you look at size, it actually decreases as you go up to the right and increases as you go down and to the left. Because on the opposite end of the spectrum, as you go down and to the left, you have things that have a smaller effective nuclear charge, which means their outer electrons are not going to be pulled in close to the nucleus. They have low ionization energy, which means go ahead and take my electrons. I'm not going to fight you. They have low electron affinity and electronegativity, which means they are not looking to gain electrons. And all that's going to do is just keep those electrons further away from the nucleus. They're not going to gain any more electrons, and they're going to have a larger size. So how does all these periodic trends sort of relate to each other? If I draw my wonderfully, and here you can see, obviously, in terms of atomic size, smaller up to the right, larger down to the left there. If we just tip all these periodic trends together on a giant periodic table here, also known as a giant box, fancily drawn. Again, up and to the right, we see Z effective increase and decrease coming down. We see ionization energy increase up to the right, decrease down. We see electron affinity increase up and to the right, decrease down. We see electronegativity increase up to the right on the periodic table, decrease down. And lastly, we see size decrease up and to the right and increase as we go down. So what we see with all this is as we look to the upper right of the periodic table, we again have things where electrons are close to the nucleus. They do not want to give away their electrons, and they want to take other people's electrons. This is what we see with nonmetals. This is why nonmetals typically like to gain electrons, because they have all those trends of, I'm keeping my electrons and I want to take your electrons, basically. When you go down and to the left on the periodic table, you have all of the periodic trends of, I don't want electrons. I don't even want my electrons. If you ask me nicely, you could take my electrons without a big deal. You could have them. And that's why things down and to the left on the periodic table, where we find metals, typically like to lose electrons. And that is why metals make cations, a positively charged, because of these periodic trends. And that's why on the upper right there, nonmetals typically will gain electrons and become negatively charged and make anions. That is also why where I circled, you find the most reactive of the two. Upper right corner of the periodic table, you have all of those periodic trends that say, I'm going to take any electron that gets near me. I'm going to keep my electrons, makes it really, really reactive. Bottom left of the periodic table, they have all the trends of, I'm going to give away my electron without any worries. Just go ahead and take it. And that makes it very, very reactive. So that's why on the kind of the bottom left and upper right, we find our most reactive metal and non-metal respectively because of these periodic trends. Any questions on those periodic trends there?